Right, ladies and gentlemen, we are busy with Chapter 8. We are making use of the textbook of Cengel and Ghajar, and we are busy with internal forced convection. Just going back to the previous lecture, was in general paragraph 8.4, which was a thermal analysis, and we've said that specifically when we consider laminar flow, then it is very important to distinguish between the fact if the heat transfer is at a constant heat flux and or if there's a constant wall involved. Of course, the characteristics of the heating or heat transfer processes are quite different. With a constant heat flux, the fluid average temperature is going to increase linearly, and we can make use of the temperature of this equation to determine the temperature along this line. It's a straight line, so it is very easy to determine the temperatures, and therefore since we've got these temperatures, and if we want the heat transfer coefficient, it is very easy to calculate the heat transfer coefficient for that type of case. The other case which is not so easy is that of a constant wall. If that is the constant wall and that's the inlet temperature, then in the beginning there will be a big temperature difference, but as this fluid is heating, the temperature difference becomes smaller and smaller. And for that reason, using the bulk temperature here as the average between these two temperatures, that temperature difference is not a good representation of what actually happens. We need to go through a derivation to be able to calculate this temperature at any specific point. Because we can calculate it at any specific point, we can of course calculate it for a certain length L at the outlet, and just where we've got the X, we need to substitute L. P is the perimeter, so L divided by the perimeter is the surface area of the heat transfer. Then we can do it with that equation, and the result of that equation is e to the minus NTU. In your textbook, they do not really use this. It is being described in the textbook and it is being used, but it's not going to be as used as much as I'm going to do it. So this is known as the NTUs, and it tells us a lot. I always first calculate the NTUs and not do this calculation directly, because it tells you a lot. If the NTUs are very, very small, then you can know that there's not going to be any heat transfer almost at all. So this inlet temperature will be equal to that temperature there. This was done for a case where the inlet temperature was 20 and the wall temperature was 100. As we start increasing the NTUs, if the NTU starts getting to 3, then we get to an outlet temperature of 96, which means we are sort of, depending on how you calculate it, within 4 or 5% of the solution, which is very good. But if our NTUs is larger than 3, then usually you've got an over-designed area, and you are wasting material, and normally you will not be very competitive in industry if you want to sell that, and or if you spec that in a design, you're going to buy equipment that is much more expensive than it needs to be. So you have to be careful for any NTUs larger than 3. So try to avoid that. So those are the two very important cases that we have to consider when we have problems where we've got laminar flow. Let's look at an example. And this example is of an icy lake. And underneath this lake, we've got oil which is being pumped. The inlet temperature is 20 degrees Celsius, and the velocity is 2 meters per second. The diameter of this pipe is 300 millimeters, and the distance is 200 meters. We need to determine the outlet temperature of the oil, the work, the heat transfer rate, and yes, the work required by the pump work. Right, let me repeat again. We've got oil which is pumped through an icy lake. Inlet temperature of the oil is 20 degrees Celsius. 2 meters per second. The icy lake is of course at 0 degrees Celsius. The pipe or tube diameter is 300 millimeters. The length is 200 meters. And we need to determine the outlet temperature, the heat transfer rate, and the work required. The properties of the oil, the question is, inlet temperature is 20, we do not have the outlet temperature. So the properties of the oil, we normally do it at the bulk temperature, and the bulk temperature is the inlet temperature and the outlet temperature divided by 2. We've got the inlet temperature is 20, but we do not have the outlet temperature. So you can go and choose whatever you want. I will most probably look at this problem and choose it at 10, which is sort of the average between the 20 and the lower limit, but you can choose whatever you want. I'm going to use 20 degrees Celsius, which is maybe not a good temperature to start with, but in this specific case you will see that it is. But you can go and redo the problem with 10 degrees and 0 degrees, and you will see that it is not that much dependent on that. You can work out the problem, get the outlet temperature, get a new bulk temperature, then based on your calculation, and just repeat the calculation. And normally you do not have to do it more than twice before it is fully converged. Okay, now the properties we can get in table A13, and they give the properties there for engine oil, so let's use the engine oil. They didn't really say what type of oil it is. And from that, at 20 degrees Celsius, I got the density as 888.1 kilograms per cubic meters. The thermal conductivity as 0.145 watts per meter degree Celsius. The kinematic viscosity is equal to 9.429 multiplied by 10 to the minus 4 square meters per second. Cp is equal to 1880 joules per kilogram Kelvin. The Prandtl number, for those of you who have your textbook here, I would really appreciate it if you can open it, because there's a lesson to learn. The Prandtl number is 10.863, and yeah, that's it. Those are the properties. For those of you who've got your textbook here, can you please take a look at it and see if you agree with me. Properties, let me just repeat it for those of you who can't read my handwriting. The density 888.1 kilograms per cubic meters. Thermal conductivity K is equal to 0.145 watts per meter degree Celsius. The kinematic viscosity 9.429 multiplied by 10 to the minus 4 meter squares per second, and Cp 1880 joules per kilogram Kelvin, and the Prandtl number 10.863. You happy with that? Okay. Now, Let's calculate the mass flow rate. Mass flow rate is equal to the density multiplied by this area through which it flows multiplied by the velocity. The density is equal to 888.1. The area through which it flows is pi divided by 4, 0.3 square, multiplied by the velocity, which is 2 meters per second, and that is equal to 125.6 kilograms per second. Once you start doing many of these problems, you will realize that one of the first things you always want to know is is the flow laminar or is it turbulent? So far, we've done only the laminar flow. After this problem, we are going to do the turbulent flow. And then you'll see that there are different equations and approaches to be used. So that is a very important information that we need to get. Is the flow laminar or turbulent? How do we do that? By calculating the Reynolds number. The Reynolds number is equal to rho Vd divided by the viscosity. Or you can write it as the velocity, the diameter divided by the kinematic viscosity, or it's equal to 4 times the mass flow rate divided by the viscosity by d, just as you want to. And if you go and calculate it, I'm not going to put in all the values because it's very simple. The Reynolds number is 636. It's a circular tube, means the flow is laminar. Because transition for a circular tube happens with the Reynolds number approximately 2,100 to 2,300 approximately. Okay. Now, something that we also need to know is how long does the flow to take thermally fully developed? And that is equal to 0.05 Reynolds Prandtl multiplied by the diameter. The Reynolds number is 0.05. It is equal to 0.05 multiplied by the Reynolds number is 636. The Prandtl number is 10.863 divided by the diameter, which is equal to 0.3. And that is equal to 103.6 meters. 103.6 meters. Okay? Now take note, this length is 200 meters. Do you agree up to now? I hope there's somebody who do not agree with me.
Prandtl number is actually 10,000.
Yes. So you have to be careful in some of the textbooks, especially the American textbooks. This Prandtl number is actually 10,863. It's not, the comma there shows 1,000. So it is 10,863. And coming back to this, it's not 103.6 meters, because this is 10,863. That would be equal to 103.7 kilometers before it's fully developed. 104 kilometers. Okay. So, if we now would do this problem according to scale, in terms of looking at the heat transfer coefficient, this is 103,700 meters. Okay. So after 10,307 meters, the flow will only be fully developed. Okay. And I forgot to mention, if the flow is fully developed, the Nusselt number is 4.36, and in this case, it is equal to 3.66. Okay. So, is the Nusselt number equal to 3.66 in this problem? The answer is no ways. There is 3.66. It will take 104 kilometers. We are at 200 meters. I can't even show 200 meters on this. So we have, so the heat transfer coefficient would actually do something like that. There's fully developed flow. Okay. So we are working there. So we've got developing flow. Developing flow, not fully developed. For those of you who can't remember, FD is fully developed, and to that side would be developing flow. Now there's not a derivation for it, given in the textbook in any case, but for developing flow, there is the Edwards equation, and the Edwards equation says the Nusselt number is equal to 3.66 plus 0.065 multiplied by D of L multiplied by the Reynolds and Prandtl number, 1 plus 0.04 D divided by L Reynolds Prandtl to the 2/3. If you look at this equation carefully, then if L starts becoming very large, then this term would go to 0. You see that? If the length is very large, then that would go to 0. Again there, that one will go to 0. So it means that you're going to get 0 divided by 1, and you start getting the answer of 3.66. See that? So that is where this equation comes from. Now you can also write this in terms of the Ghajar's number, which is equal to D divided by L multiplied by Reynolds Prandtl. And then you can write this equation as Nusselt number is equal to 3.66 plus 0.065 multiplied by the Ghajar's number divided by 1 plus 0.04 and the Ghajar's number to the 2/3. Okay. Now I'm not going to put in all the values here. You've got the Reynolds number, you've got the Prandtl number, you've got the diameter is 0.3 meters, the length is 200 meters. So the Nusselt number, take note, is 37.3. So it is significantly higher than this value of 3.66, which is valid for fully developed flow only. And that is why it is so important to know if the flow is fully developed or if it is developing. Right, if this Nusselt number is equal to 37.3, then we can calculate the heat transfer coefficient by saying the Nusselt number is equal to the heat transfer coefficient multiplied by the diameter divided by K. The Nusselt number is 37.3 is equal to the heat transfer coefficient 0.3 divided by K, which is equal to 0.145, from which you can calculate the heat transfer coefficient as 16.3 watts per square meter Kelvin or degrees Celsius, whatever you prefer. What do we need to calculate? We need to calculate the outlet temperature and the heat transfer rate. So if you get the outlet temperature, it is very easy to calculate the heat transfer rate. We do that by using this equation. Okay. for a constant wall temperature, because we've got a constant wall temperature problem here. So the outlet temperature is equal to Ts minus T in multiplied by e to the minus NTUs. The NTUs is equal to, if you go and calculate, okay, let me just write it out. It is H Px divided by the mass flow rate and Cp. The heat transfer coefficient is 16.3. The perimeter is pi divided by the diameter. Okay, pi divided by 0.3. Multiplied by the length is 200. So this gives me the surface area of heat transfer divided by the mass flow rate, which is 125.6, multiplied by Cp, which is equal to 1880. And that gives an NTU of 0.013017. What can we learn from this NTU value? Going back to, if the NTUs are low, then there's almost no heat transfer. The temperature is not going to move. Okay. And that's the reason why I've selected to get my properties at 20. Okay. So if you go and calculate the outlet temperature now, is then equal to the surface temperature is 0 minus 20 e to the minus NTU 0.013017. This equation is that equation there that I'm just implementing now. Then you can calculate the outlet temperature of the oil is 19.74 degrees Celsius. So the oil temperature is not really going to change over 200 meters. Okay. Now, if you want to, you can now say, let me go and recalculate the bulk temperature. Is 20 plus 19.74 divided by 2, which is now going to be 19.8 or 9 degrees Celsius. You can go and get the properties now again at that temperature, and or you can do interpolation or extrapolation to get it more accurate, and you can repeat the problem. Okay. Any questions? We are not finished yet. So in terms of the outlet temperature, that's the first part of the problem that we've now determined. Let's calculate the heat transfer rate. Right, the heat transfer rate is equal now to the heat transfer coefficient multiplied by the surface area multiplied by Ts minus T bulk. Okay. It's equal to the heat transfer coefficient is equal to 16.3. The surface area is pi multiplied by the diameter multiplied by the length is 200 divided by the surface temperature is 0 minus the bulk temperature, which is now equal to 20 plus 19.74 divided by 2. Yes, there was a question there at the back.
Is the delta T and TDA?
Good, thank you. I was hoping somebody is going to pick it up. Incorrect, okay? Incorrect. When we've got a constant wall temperature, using this temperature difference is incorrect. You need to calculate the LMTD. Okay? The LMTD, and or you can get it from In this case, now that we've got the outlet temperature, you can just say it is equal to m dot Cp multiplied by the temperature difference. But I'm going to use the LMTD now. In terms of the LMTD, students find this thing very complicated, but it is very simple. So how does it work? The inlet temperature is 20 of the oil. It's going to exit at 19.74. That's the oil. Okay? The surface temperature remains constant at 0. Calculate the LMTD. It's equal to, and all of you finish your writing up to here so that you can see what I do and not just write it down, because if you just write it down, you're going to miss how really simple it is. Okay. Right, the LMTD is this temperature difference here on the left. It's 20 minus 0. Okay? Minus the temperature difference here, 19.74 minus 0, divided by the ln of those two terms, the left-hand term and the right-hand term. Okay. So it is this temperature difference on the left-hand side minus this temperature difference on the right-hand side divided by the ln of those two terms. And the temperature difference is then going to be 19.87 degrees Celsius. Now, calculating the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by LMTD. The heat transfer coefficient is equal to 16.3. The surface area is pi multiplied by 0.3 multiplied by 200. LMTD is 19.87, and that is equal to 61.1 kilowatts. Right? That is the one way that you can use to determine the heat transfer rate. You could have also said it is equal to the m dot Cp multiplied by the outlet temperature minus the inlet temperature. It's always good if you can double check it, and you can make sure your answers are correct. You've got the mass flow rate, you've got the Cp, you've got the outlet temperature, you've got the inlet temperature. So I hope that would also work out as 61.1 kilowatts. You can go and check. Right, there's one more thing that we need to calculate, and that is the work of the pump. For the work of the pump, we need the pressure drop. For the pressure drop, we need to get the friction factor, 64 divided by the Reynolds number, 64 divided by 636 is equal to 0.1 approximately. So the pressure drop is equal to the friction factor multiplied by L of D multiplied by rho V squared divided by 2. All the values are here on the board. You can just go and put it in and you'll get the answer of 119 kPa. The work of the pump, I don't know which terminology you've used in fluid mechanics, but it is the volume flow rate multiplied by delta P, or it is equal to the mass flow rate divided by the density multiplied by delta P. You can use whichever one you want, prefer, and if you do the substitution, it's going to be 16.8 kilowatts. All understand? Yep.
So is this formula only, can you only use it when it's developing, or can you use it in any phase?
That's a great question. In your textbook, so just like with the heat transfer coefficients, the friction factor also does that until it's fully developed. So this equation in your textbook is for the fully developed part. It doesn't take this into consideration. So you should actually go and get that average, which is much higher than that value of 0.1. But your textbook doesn't cover it. Okay? But it is good to remember that. Okay? Any other questions? Right, now let's go to paragraph 8.6, which is turbulent flow. Turbulent flow in pipes. Now, if you've got your textbook with you, then I would recommend that you keep it open because there are quite a number of formulas that's going to come now. Okay, why such a, this is the, quite a number of formulas. Why? Because tubes are the most important things to be considered. And a lot of work has been done for that. But it starts with what is called the first Petikoff equation, which was developed in 1970, which is valid for smooth tubes, and it gives the friction factor as equal to 0.790, the lim of the Reynolds minus 1.64 to the power of minus 2, and it gives a Reynolds number range of, it's valid from 3,000 to 5 million. And that is called the first Petikoff equation. Now one of the first equations that were derived to determine the Nusselt number in a tube is this very simple equation. It is Nusselt number is equal to 0.125 multiplied by the friction factor, the Reynolds number, Prandtl to the third, and that is from the Chilton-Coulton analogy. And to that equation, that is with the friction factor being calculated as 0.184, Reynolds to the minus 0.2. Okay. And then after that follows the Kolben equation. The Kolben equation is equal to the Nusselt number is equal to 0.023, Reynolds to the 0.8, Prandtl to the third, and again, there's a range for the Prandtl number and the Reynolds number to be used. The values are in your textbook. Okay, now these equations are all equations 865 to 873 in your textbook. They're all summarized there together. Okay. Then Dittus-Boelter developed this equation, and they said, now wait a minute, this is actually, we can do it better by writing it as 0.023, Reynolds to the 0.8, Prandtl to the n, okay, where n is equal to 0.4 if we are doing the heating of the fluid, and n is equal to 0.3 if the fluid is being cooled. And that was a more accurate description then. And then Kolben came and said, but okay, this equation works well except when we have huge heat fluxes, and then we need to refine it, and the equation develops to Nusselt number is equal to 0.027 multiplied by Reynolds to the 0.8, Prandtl to the third, and then the viscosity bulk divided by the surface viscosity to the 0.14. And again, it is valid for a certain Prandtl number range and a certain Reynolds number range. So what is now different is for the first time, it introduced what we call changes in fluid property with this term. And in many cases, if they just give this equation, students do not know, well, which one of all these equations should I use? And a few other equations are going to be followed. So my recommendation is you need to look at that ratio of the viscosity. Normally, if the temperature differences are in the order of 10, 20, 30 degrees Celsius, then that ratio to the power of 0.14 is going to end up as 0.9 something, 0.95, 0.99. So it is not going to influence your results. But if there are huge heat fluxes, so if the temperature differences are maybe 100 or 50 or 200, then this term is going to be very important. What is the difference between this? Because this is the fluid, which is the bulk viscosity, and that would then be the viscosity on the surface. So you need the surface temperature, you need to be able to get the bulk viscosity in, and if that ratio starts becoming, and to the power of 0.14, if it starts becoming less than 0.9, 0.8, 0.6, then it is very important to take that into consideration. Again, depending on the type of design that you're doing. Okay, then comes the second Petikov equation. Now, why is it called the second Petikov equation? Because this equation is also known as the Petikov equation, but that's for the friction factor, and that is for the Nusselt number. I'm not going to write down this equation. And then the last one, not the last one, but one of the last ones, is then called the Gnielinski equation, which is equal to the friction factor divided by 8, Reynolds minus 1,000, Brownell to the 1 plus 12.7, friction factor divided by 8 to the 0.5, Brownell to the 2/3, minus 1, and this is also valid for a certain Brownell number and the Reynolds number range. Right, so we see that the Nusselt number is a function of friction factor, Reynolds number, and Brownell number. This equation, it is unknown how accurate it is, but in general, people would say it is less than 20%, or within 20%, maybe 10%, but this equation is sort of the most accurate of all of them. Then after that follows liquid metals, equations for liquid metals. I'm not going to write it down. It is in your textbook. But then there's a very important sentence there somewhere in the fine print. And that sentence says that if the flow is turbulent, then the boundary condition of a constant wall temperature or a constant heat flux is not important. So how the heating or cooling occurs is not important if the flow is turbulent. Any questions, ladies and gentlemen? Well, the question that you should ask is, well, which equation should I use in the test or exam? Isn't it? Well, the answer is, normally you can use whichever one you want. I'm very lazy, so I will most probably use this one. Okay? Except if you need to do a very competitive design. Let's suppose you are competing against other people for a big tender. Then getting this as accurately as possible can have a huge influence on the cost and or the fact that maybe you get the tender and then you discover that you're not getting enough money to produce what you should produce. So if you need to be very competitive, I would go for this equation. If it is about back of an envelope type of calculations, then I will go for this equation, which is the simplest and take the less time. Right, if there are no more questions, then ladies and gentlemen, thank you very much.